Let's continue our series about reinforcement learning for animation. And this time we'll be looking at a paper that has a continuous state space and a parameterized action space. So for each action, instead of just being able to play one clip, we will be able to select several of them and blend them together. Hi, I'm Jerome, and today's paper is Real-Time Planning for Parameterized Human Motion, a paper from 2008. As usual, what I will do is that I will import a bunch of libraries I need, and I will import my characters, sets of mesh to represent the direction and the targets. And what I will do is that for the animation data, this time, instead of using Lafan animations, I will use Motorica AI website to generate a bunch of locomotion animations. So the websites allow you fairly easily to just select the trajectory that you want to see and then generating an animations for it and to export that animations. The free tier allows you to generate up to 10 seconds of animations. So a lot enough for what I need to do here. So what I have is that already a bunch of animations and that I have retargeted on my character. And so if we check those clips that I have, is those ones. So I got a bunch of turning animations like this, and I will have a few of turn animations and then start and stop. So I get 46 different clips like this. And this paper builds on top of the previous near-optimal character animation with continuous control that we did before. So it uses exactly the same concept for slicing your clips into small steps and realigning all those steps every time. Those clips every time you want to pick an action and play the next clip, you align both. So I will not go through that process again. It is exactly the same process as the near-optimal character animation with continuous control paper. So go watch that video if you want to see exactly how those clips works. So the only thing I would do is that I would basically regenerate all the motion clips and go back to the stage we were with the previous paper, which is this. Every clip is something like this, a small step, and then so you get the first contact next, and then it stops there. So every clip is this, and then you will be able to play with them putting them back to back. So I got a bunch of clips doing all the different rotation and turns and all that kind of this stuff. So that's the animation data. That's the clips of the animation data we'll be using. So what I will have is, as usual, I will have a player that's allow me to just say, I want to play this clip after that one, and so on, and keep track of the positions and realign all the clips automatically. So I'll load that code. And just to show you exactly as before, what I can do is I can just set the player to randomly pick a clip every time, and you get this basically. It just randomly picks clips, and you can see that it could generate fairly continuous motion with no foot sliding, except that it goes. It might have discontinuities completely between clips, but the player is still able to do what we were doing in the previous paper. And following the exact same system as the previous paper, what we need to compute now is computing the physical continuity between each clip. So basically making sure that when we pick a motion and we pick a clip after another one, it is physically plausible. Also make sure that we never pick the wrong foot by giving a really high cost of playing a clip that is on the wrong foot. And also taking that time to compute how much playing a clip after another one will actually rotate the character and will actually move the character X and Z position. So all this code is exactly the same as the previous paper, no difference here. So I've just run it before, and I will just reload some of the stuff that I've created. So right now I have a big table that gives me the physics costs from any clip to any other clip. I get the delta, the rotation delta from any clip to any other clip, and the same for position X and Z. So we have the exact same features that we had previously. Now, what we want to do is actually train an optimal policy trying to match a goal. And the first goal we will try to match is the easy one, is to make sure that the character I control goes in the direction I want him to go. And for this, the paper it's fairly similar to the continuous control. It's just take a different approach on the approximations of the value function. So if you remember the previous one, we were using basis functions to approximate the value functions. And why we had to do this is because the value function is inside of a continuous space. So it's hard to train it on every possible values. So what we do is that we train on a subset, and we try to approximate the value function as best as we could with something that will give us what we expect the value to be outside of the value we've truly seen. We did it with basis functions. And basically what this is called usually, it's a regression. So what you have is a function that you don't know, a bunch of points on that functions that you do compute, and you try to regress and find an approximations for the function itself. So basis functions was one way of doing it. This paper decided to go with extra tree regressors. And why they've picked it is because it's a known regressor. It's good at giving you an approximation of any functions when you throw a lot of data at it. And the advantage of an extra tree regressor compared to the basis functions is that it is able to approximate anything without a prior knowledge of what the value functions should look like. If you remember when we did it with basis functions, what happened is that you do have to kind of guess what the value function would be to figure out what is the basis functions you want to use to address and to approximate them. Here, you could just throw a regressor at it and see what it would learn from it. It has a little higher cost in memory, of course, because it has more parameters to learn and memorize than just the few basis functions you could use. But it's also better at learning value functions that will not be extremely smooth. What happened is basis functions, we assume that the value functions will be quite smooth, and then we could just use a bunch of Gaussian values to approximate it. The regressor, the extra tree regressor, will just accept any shape without assuming that it will be smooth or anything. So that's the first difference between the two papers. They use a different type of regressor. In my case, I will use the extra tree regressor from SciPy directly because it exists. I know that it's stable there, and I could just use this one. They do implement their own with some specific mathematics behind it. I will not go into details with those. I will just use the regressor. Okay. Let's go through how to train the optimal policy. It is fairly similar to the previous system. So what you do is that you start with an empty value functions where everything is 0. So basically, you have no knowledge of what the value function will be. You set it all to 0. And you start to create a training set out of all the possible states you could have. So the way you do it is that you randomly start at any in any states, and from there you use your optimal policy to traverse, to start from that states, and you just use the policy and see what you get as results. And for all the steps you take, so you basically move forward as if you were playing. And for all of those, you store the pair between the states and the reward that you would get from taking that action. So you store the states and reward that you encounter while traversing your states. Once you have all of those, when you have a set of those, you train your extra tree regressors to approximate all the value functions. So you get a new set of value functions. And you re-update all your pairs you had. So basically, you've computed states and reward, states, reward, states, reward. You recompute the value functions, and then you go back through all the states you've seen. You retake the best optimal trajectory you could have taken, best optimal action you could have taken from there. You get a new reward, probably, and you update the values, and you do that for each of them. And when you've done this, you start the loop again. You reset a bunch of random starting positions, walk through and get a few new trajectories that should probably be better because your value functions get better and better every time. And you keep repeating this until you get convergence. What they would do is that they will stop getting new data at some point, and then they will just train the value functions on itself with all the data they have. Let's not spend too much time on that detail, but yeah. Usually that's how you do it. It's the loop of getting a bunch of data, training your value functions, updating all the data you had, gather more data, and so on until convergence. And to check that you have converge, we compute the Bellman residual, and it's just a computation of knowing these states expected last time this reward. And if I actually take my policy, it gets that as a reward, and you check the difference between the two. And the goal is to have zero difference, to get the expected reward being exactly the reward you are waiting for. So that's it. That's how the algorithm will work. And now we will train this and see how we could do it. So I will do it for the example of rotating my character. And so the only where is the reward? Fairly simple. Yeah, that's there. So the reward is, as before, is basically I will encode everything as saying that my character should walk forward inside of a state space. So the state space is always local for my character. And the only thing I want to do is to make it sure that it walk forward inside of the state space. So basically anything that tells me that it is an angle would say that's the offset that's making me not walk in the direction I want it to walk. So the only thing I compute is the angle of my character local to itself where it end up walking. So that's my states, is how much rotations, offsets I want to have compared to in front of me. So I will have a transition function that is just able to say, I'm in this clip with a plane on X and Z positions, and I get an angle relative to my plane. And I want to play the next clip to that, and where that will bring me, that's basically what it returns me. It returns the next clip. the next x prime, the next z prime, and the next theta prime, the next rotation. So the transitions basically is computed the same way as it was done in the continuous state space. I get the transition reward is what is the reward of taking one of the actions. So basically, if I'm in specific states and I want to go to the next states, what is the reward of doing that? And basically, in this case, the reward is negative, is the inverse of the cost. So the bigger the cost, the more negative that reward is. And the state reward is just the reward of being inside of a state itself. And that state reward, what I will do is that I will say anything that is over the original animation number 25 returns a big negative score. And that's just because I know that all of my animations I've done here is, see, I get the walking in curve, I get a bunch of turn, I get the walk forward, and then everything else is start, stop, slowing down and stops. So I'm in a controller that where I just want to walk in a specific direction. So basically picking any animation that is not a walking animation is a big negative reward. And apart from that, where am I here? Otherwise, I just check where this state will bring me relative to where I want to walk actually, and that's it. I will just return the absolute angle. So if my states make me walk in the direction I want it, that's basically a reward of 0. Otherwise, it's a negative reward of how much disalignment you have. So fairly straightforward for the rewards and that kind of stuff. What I will have is how to pick to read my value function compared to theta primes and the clip ID. And here is the stuff that I've done a little differently than the paper. The paper is using an extra tree regressor and then is just using it directly to get the value. What I wanted to do here, it was to be able to use NumPy and the vectorization of NumPy, so I could basically request the value functions for every state in one go and having all of that computed in parallel, which is something that is fairly hard to do with the implementation of the extra tree regressor in SciPy. I mean, that's one tree that runs on one core and so on. So what I've done is that I would compute the value functions, the extra trees regressor, I will compute all of them. And then once they compute it, I will pre-compute a search table. So basically I will use the value functions and I will say, that's nice, you have an extra tree regressor that gives me an approximation. Now just give me a big table of pre-computed values so I could just pick the closest one. And at least I can do that in parallel for all the clips in one go. So that's why I have here the value functions actually are not the trees exactly. They are one big table with a bunch of pre-computed values for me. And so that allows me to find easily all the indices that I want to search inside of that table and then to return the values of that table. And I use optimal policy then basically is just taking the starting clip I have and picking the transitions from the starting clip towards all the clips at once. So taking the transition between my clip and everything else. That's giving me the X prime, Z prime, and theta prime of all the possible transitions. Then I compute the transition rewards for all those different transitions. And then I can compute the future reward for all of them again, multiplying by the discount factor. And once I have that, I just pick the one that has the higher score. And then what I return is the picked one, the new x prime, z prime, theta prime, and the reward. And this time in the reward, I picked the transitions plus the future reward. So that's basically the future reward. And I'm adding the state reward to it because that state reward doesn't change anyway. It's the reward of being in my state now, not the reward of being in any future states or anything. And so that's the value functions and the policy itself. I will not care about this one. And so what happened is now I could do the algorithm of trying to train that value function. And see, it's done the way the paper describes it. So basically, I take 800 random starting positions. So I picked randomly any clip and I pick randomly any angle, and that becomes my state. So one clip, one angle, that's my state. And then from that state, I use my optimal policy to get the next clip, and I store my state in the X. So I store my current clip and theta, and I store the associated reward for it. And I keep this for 10 steps. I keep walking using my optimal policy for 10 steps and recording every pair of state reward. And once I have that pairs of state reward, I train for each of my clip, I will train an extra tree regressor. So it's the same concept as the continuous character control. You have one value function per clip. So basically it is a continuous state space where the clip itself is tabulated. So you learn a bunch of continuous state space next to each other and a bunch of value functions next to each other. So each clip has its own value function into a continuous value functions, and then you train all of them at the same time. So because you will start from one clip, then read the value function of the other one, and so on. So you have to train all of them at once. Consider them as one big value functions, except that the clips are tabulated. So compute the extra tree regressor with all the pairs of states and reward. And as I said, what I do after that is that I predict a bunch of values, because that is again vectorized and parallelized fairly well. So I can predict, I think I predict 300 different values for each of my trees. And I put all of that into one big table. So I will be able to use NumPy to do computation in parallel on that big table. And so once you've done this, what you do is computing the residual. So how much errors you have between what reward I was expecting before and what reward I receive now that I've updated my value functions. And at the same time, I update the expected return to be the new expected reward, basically. So that's the expected reward for the next iteration now has been updated with the new rewards I have now. Again, I've run this before, and I will just reload what I've loaded. And what you could see is that I haven't done a lot of epoch because basically it's fairly easy to learn in this case. What you see is the mean error, the mean residual, Bellman residual. So it drops fairly quickly, and I get the maximum residual error. So also dropping. So between the best expected reward and what I actually get, I don't have a lot of difference. Let's say I can now have gamepad, and I can start to play with what we've learned here. And so now every time I rotate, it will just use the same optimal policy of checking every possible clip, checking the future reward to see how good this gets. And so we have something that is fairly close to the continuous control, except that I would agree that using the extra tree regressor was a lot simpler to use than trying to find what would be the best basis functions for the value functions. And it's quite responsive. You could tweak if you wanted to learn something a bit more responsive, and by giving less score to the physicality continuity, but it does work. Now, what this paper shows is that learning with extra tree regressor was needed if they wanted to do, in their case, they were doing grabbing animations. So giving an object, ask the character to move toward that object and grabbing it. I don't have grabbing animations, so what I would do instead is stopping at a specific target. So I will give him a target somewhere in the world, and I want the character to walk toward that target and stopping on the target. It basically gives the same concept. It's maybe a little less visual, but it's still working. So what I will have is what I call the reach goal policy. So I have a bunch of animations that are stopping animations. So I know which one they are. So that's all my stopping clips. Those one with just the two-step stops at the end. Now, the only thing I need is to know, I will ask it to stop at a specific position, which means that by the time I take the decision, I need to make sure that take the decision that if I play that clip, it would stop where I want it to be. So I need to know what is the state in which I need to be to actually make sure that if I play that stop, I will stop where I want it. So that's the stop positions. It's basically give me where I actually need to be when I take that decision to play this clip, so it would just finish the animation in the right spot. So that I compute basically where the stop needs to be, starting to stop at 0, 0, 0. Now, the reward function for this system normally is this. As they said, you basically give it just a reward. If you are stopping in the right spot, you get a reward of 1. And every time you do not, your reward is 0. Basically, that's a sparse reward function. So it means that there is really not a lot of time something that gives you a reward. So they say in the paper that you could just train with this reward functions and that would work, and that's magic. It's something that is known to be extremely hard to train, actually. And with the data I have, I was not able to just hope for the best, like they were saying, and then make it work. Because what happened is that you have two cases, basically, and you have to find the right balance between the two. If your reward from reaching a certain position is really big, what happens is that it would transfer that value through your value functions through every state near it. So everything will say, it's really important for me to reach that point. I don't care if the transition cost is really high, if all my feet are sliding, if I pick the wrong clip, as long as I'm reaching that reward, That's what matters. So that's what happens if you give your reward for reaching a value that's too high. On the other hand, if your reward value is too small, basically what the system will learn is that everything is bad anyway. There is no reward of walking more in a direction than anything else. So what it will learn at the end is that as long as everything is negative anyway, let's pick the one that give a nice continuous animation, and I don't care if I reach the goal or not. And you really need to fight between those two. And it's really hard to find the right values that will actually let the value functions learn exactly how to get there. Especially because in my case, I have 200 clips, I think, and I only have a few stops. So really not a lot of stopping clips. So it's really sparse in my case. So I was not able to train my value functions just by doing this. So there is a bunch of tricks you could apply when you try to train a sparse value functions like that one. So what I would have to do to train these value functions, I would not be able to just let it hope that it will find something by just stumbling upon one positive values and then hoping that it will start to learn that maybe going that direction is the good way. So what I would do is that I will add a bunch of tricks that you could use when you try to train values like this one that has a really sparse reward. The first thing you could do is to have a bootstrap. So basically, instead of starting from nothing, start from something that knows it works. So what I would do is that I will give him a bunch of known trajectories that are actually reaching the goal. And I'm starting from those trajectories instead of starting from nothing. That's the first thing. The second thing I realized that I needed was the fact that although it was able to find the target when it was fairly in a certain area around it, when it was too far from it, I had nothing that was forcing him to walk back in the right direction. So I would also add a penalty of being too far away from the goal. So basically it would force the system to say, if I'm really far, it's better that I walk in the direction of the goal. And then as soon as I'm close enough, I will find the best trajectory to reach the goal anyway. But I actually had to have those two different costs. One that's trying to get to the goal and one that's really far. You try to walk towards mainly the goal. And then the last thing I've done is instead of telling the system that I want him to, every time I get the new reward, instead of setting that value for the new reward, I was using a temporal difference. So I'm only computing the error I have between the expected reward I wanted and the true reward I wanted. And I'm only slightly updating the reward, the expected reward. Instead of just replacing it, I just said I take 10% of the new reward and I lump 10% of that new reward. And that's how I managed to make this learn. So basically, the transition functions is a bit different because before everything was local to my character and I was telling the character that it has to walk forward and that's it. And I was computing the angle. This time, every state encode in the position X and Z where the target is. So if my character is here and the target is here, that's what it's encoded. If it walks like this, basically the new values is this offset. So everything is always realigned to the character. So my target is always represented as a local offset from my character. So I get my transition. What I will have is an inverse transition functions, basically computing the exact opposite of this one, saying that if I'm now in a specific state and I was coming from another state, where was I? That's what the transition inverse does. I get the transition reward, same as before, as the physics costs, and inverse the physics costs. And I get the state reward, and the only thing that the state reward does is this. If I'm playing a stop animation, I'm just checking, am I in an area of a radius of 50 centimeters around where I wanted him to stop? And if it's the case, you get a reward of 1. And if you ever pick that state reward with that stopping animations while you actually do not stop in the right spot, you get a massive negative reward saying that that was not what I wanted you to do. Never stops outside of your stopping animation. And that's where for all the other case, if I'm really far from my goal, I get a little penalty from being too far. That's it. That's my state reward. I still get my value functions. Instead of now, it's an X and Z value function, so the 2D value function. And my optimal policy, it's basically the same optimal policy as before. I take my transitions, I get the transition reward, I read the value functions, I get the value functions for it, and I picked the best one. The only thing I did, just to avoid having those massive negative values getting injected inside of the value functions, what I've done is that if I realize that it picked a stopping animation while it shouldn't have anyway, I basically restart the search for the optimal policy by removing any stopping animations from the available clip you can look at. So basically, I'm checking every clip. If it decided that the best clip it could pick was a stopping animation while it wasn't supposed to stop, I just tell him, search again, this time doesn't count for the stopping animations. So that's the value functions. Now I do need, to do that bootstrap. So basically what I have is a system that allows me to roll back trajectories. I can say I'm starting from one position and I walk backward from there. That's what the rollback trajectory will do. And so for instance, let's pick this one. I get all my stopping animations and I will roll back 8 steps. And you can see, basically that's the kind of stuff I will start the learning from. I have all those different trajectories that will eventually, anyway, stop all in the same position. So that's what the bootstrapping would do. I will have all of those trajectories pre-generated, and I can start to learn from those. So I will not run this because it would take a bunch of time. I will do this 100 times, different positions for all the stops. So it would generate 100,000 different trajectories that actually reach the end. Or I can do it, so I can show you what happens. I don't think it's that long. So I generate a lot of trajectories, yeah. And then I can display now all for every clip, so for every clip animation, you could see all those areas are all positions that I know that if I'm in that state, I'm able to reach the stopping animations. So it gives me a lot of data to start from. So I have a bunch of data that's I know that are good enough to start learning from. And so hopefully it means that every other clips would start to try to reach those points or another points further and that kind of stuff. And then I would be able to train. So the same, yeah, I can put that. The only difference this time is because it's a lot longer. There is a lot more value functions and a lot more data in all the value functions. So the only thing I've done to speed up the process is that I've starting a multiprocessing. So I will actually train the value functions in a pool. So I will actually use all my cores and all my CPUs to train it, but that's not really important. Everything else is basically the same. You know, I'm starting, so I'm bootstrapping with a bunch of known trajectories that are valid with an expected, the best expected reward I could get from it. Anyway, it's even higher because it doesn't take the transition cost into account. And then generating a bunch of new paths and then new stops. Every time you actually reach the goal, you stop because you don't want to see what happened after the fact that you reached the goal. So train the values, and it's the same loop when I'm training the values, creating the pre-computed tables and reusing them, and then recomputing the residual and all that kind of stuff. Again, all of that has been run before, and I can show you here what happened with the score and the mean value. So for every epoch, so I run it 50 epoch this time. The only thing I've done also, I've done a lot of stuff to make that able to learn. You can see that it started to learn, and so basically at every epoch, it's generating, it's around 2,600 different trajectories. And that's the number of trajectories that actually reach the goal in 10 steps while learning. You can see that it was starting to get better, but it was fairly slow. So after 10 generations, what I did, it's basically, I kept the same value function, but I made him forget all the previous trajectory it did. And I make him restart again. And you can see that it suddenly get a big jump because it has less example of wrong trajectories, and so I guess the value functions are softer and better at learning the values that don't have too much. And I tried to do it several times, make him forget again, and basically it capped at the same level every time. So it nearly reached 100%, meaning I can start from anywhere, and in 10 steps is always able to reach the stop. And I can display one of the value functions, for instance, so you could see what the value functions look like. So it's the pre-computed one goes from minus 1,000 to 1,000, and you get that there, not exactly in the middle, a bit offsets. That's where it wants that clip to be able to reach the stops. And again, I can play this. So right now it's not input anymore. It will randomly pick a positions and try to get that character walk toward that goal. And it has 50 centimeters area that are agreed to, not trying to make it get perfectly on the stop, because again, those clips are not perfect. So I want to make sure that it is still able to reach the end goal easily by giving him a bit of slack, let's say. And with all the tricks to train those value functions, it is then possible to do it. Without all those added stuff on top of the paper, I'm not sure I would have been able to learn these value functions to do this. Now, that's the default system. It basically uses the exact same thing as the continuous functions now. I'm just playing one clip and that's it. I pick the best clip to reach a goal every time. What the paper says is that what you have now is a suboptimal search because it is linked to all the clip it has, and it is not able to learn something a bit more smooth that would be able to reach more easily the goal. So comes into play the motion groups. So what they decided to do is this. Instead of picking one clip, what you do is that you regroup those clips together, and that's what they've done here. See, they get a bunch of groups, and those groups will become your clip. And inside of those groups, you have a bunch of animations that represent the same kind of stuff, and that those animations can be blended together. So you could choose to blend between your first animation and the second one, and to have all the in-betweens. So that's what the motion groups will be here. That will be exactly the same thing. I would take a bunch of indices, and I would take a bunch of weights to decide how they represents the blend between the two. And then I can show an example by picking. So basically, I picked a bunch of indices like that, and a bunch of weights, and you can see that what I have here is the same as before. I have one clip that is able to do this, but then I can actually start to blend, and it will be a bit different. And you could choose the different blend weights between the different clips. And so now what you end up with is what they called the parametrized action space, because now my action is not just the clip I had. It is the fact that each of my clip have different possible values. They have one parameters that decide how much you could tweak them. So now I actually need to build the same system as what they've done here. So regrouping all the animations together that do make sense. And for this, I had to write a bunch of helpers functions to compute the different angle of each of them and all that kind of stuff to regroup them. And by playing all of those, I've ended up with this list of motion group indices. So now those two indices become one motion group from which I can blend between the two. Those three become one motion group, and I can blend between the two animations, and so on and so on. It was basically built by hand, same way as what they've done. They're also saying that it was every clip was chosen by hand and blended by hand. And now that I have those motion clips, what I would do is I'll run that. Is define a bunch of weights for them, depending of if I have 2 indices or 3 indices. I will decide the weights on how I want to blend them. And again, why I would do this is because what the paper does, normally it picks one of the motion group, and it treats the motion group as one action that you can pick. And so what you do is that the algorithm works as before. You pick the clip, except that what they've done as once you've picked the clip, you actually evaluate the parametrized version X amount of time. So you slice it, and you take the value of 0, 1, and then 1, 0, and all in the between, and you can choose how many betweens you want, and you pick the best parametrized version you could have. So you pick the best group, and out of that group you re-evaluate your value functions X amount of time to pick the best parameter you could have. What I would do would be the same thing, except that again, I want to be able to parallelize all of that with NumPy. So I would go the opposite way. I will, from all my group, I would in advanced parameterized all of them. So I will have, I don't remember how many groups I have, but I have a bunch of groups. And for all of those groups, I would take 11 sample in between. So I would parameterize all those groups, and I would flatten all the list of parameterized group in advance, which is what I'm doing here with the group count. That returns the number of parameterized version of the groups I have. So I have now basically 847 different clip I can pick from, because that's basically what it is. It's all the different group with all the different parameters version of the group itself. While I had only 150 clips in the beginning. So I'm growing the action space basically. And then I can display all those groups I have. So that means that I get this animation, for instance, for group 0, and I can see parameterized between those two. I get that, and that's all the different parameterized version I have. So I get all my actions now, my animations are slightly parameterized. What I would do is, again, I would need to compute the cost of any parameterized version towards any other parameterized version. So basically, that's the reason why I flattened everything in the beginning, because I would need to compute the physics costs between all of the cases. What they do is they compute it at runtime only for the small groups that they know that they want to stay in. Again, I will flatten everything in advance, and I will compute everything in advance. And then the learning is all the same system. What I have is all my stop indices, except now it's a bunch of stop indices that were parameterized with different lengths, different stops. So I have a lot more different stops. Again, I will have a lot more standing position for all of those stops. And same way, I would also need to bootstrap my learning with a bunch of trajectories that I know works. This time, instead of having a lot of random positions around it and growing only a few paths, what I would do, because I have a lot more possible trajectories to start from, I will only pick one, but I will spread it a lot more. So I would say, I'm starting from here, and instead of picking the best trajectory, you give me the 20 best trajectories starting from there. And then I'm only growing a lot less further than that. So instead of having a bunch of long trajectories, now I have a lot of really small ones. And hopefully I'm still able to learn my value functions, right? That's what I wanted to get. I will not run this code because that is a lot longer. And all the optimal trajectories and all of that stays exactly the same as before. It's only my optimal policy now. It's a bit different. And it's only different for one little case, is that before, when I was getting my value function, I had one value functions per clip. Now I have one value function per motion group. That was the idea. You have one, you find the best motion group itself, and from that one, you picked the best parameterized version. So because I've pre-flattened everything, what I have now is that it means that I only need to evaluate the value function. I need to evaluate the same value functions for all my parameterized versions. So that's what I'm doing here. That's why I have that weird clip that says group count and then the clip value functions, which is divided by 11, because I know that I've parameterized 11 times each of them. So they're grouped like this. And I just need to say, okay, all those values need to check that value functions all those values need to check that value functions, and so on and so on. So that's the only difference between this version and the other versions, that a bunch of actions share the same value function. And so I need to run that. And apart from that, learning process is basically the same thing. I've trained it several times. I've tweaked a bunch of values by keeping the same value functions. So the only thing you see here in the epoch and the score over epoch and that stuff is the last time I trained the value functions, because basically I trained it with the old one and then I reduced, I made it learn really close, and then I started to make it learn further and further and further to make sure that it starts to reach. And that's what you see now is the latest run, the latest learn. And you can see that it basically, at every iterations, it adds 800 something, so the same number as group. And yeah, I'm capping around 700, a bit less than 700. So again, always able to find the spot in less than 10 steps, more or less. And I can let it play, and we could see what happens now. So basically, this time, if I let him run, that will be better. I should be better at stopping on the spot, because that's what I've learned him. I did not give him that big range of possible actions to pick from. It tries to stop exactly on the spot. Now you could see that sometimes it does big steps to reach it, and that's probably because I gave him a bunch of trajectories, and instead of finding the best closest one, it finds one of the trajectories that will bring him back where it wanted to be. But that's in a nutshell how it works. It has a hard time finding the spot when it's too close. If it walked just next to it, you would have to do a round and come back, and because there is not enough parameterized version to make short steps and that kind of stuff. But it reach more easily the targets we want him to reach. So this is the parameterized version, so continuous state space and parameterized action space that this paper give us. I hope you liked it, and see you next time.